Okay, so this is the first time that I'm going to be presenting these ideas. These are ideas that are frankly still more or less in development. 3D printing, obviously, is a I mean, compared to pianos anyway, very new technology, and so it's something that we're playing with so far with very good results. But we'll keep going. And I was up till 2 o'clock in the morning making this presentation, so kind of flying by the seat of my pants here.
We don't procrastinate here.
No, not at all. Okay, so 3D printing, just kind of brainstorming some ideas of why to bother with it. Did everybody see the 3D printing room? Mm-hmm. So you see, so how many people are familiar with 3D printing? I know Adeline is. Yeah, Bryce, you are, Scott. And then a few other people, and then Jake's done some here. Okay, super powerful technology in so many ways. There's two main different types of 3D printing that we do here. There's filament printing, and then there's resin printing. So filament printing, the advantage is it's really fast and it's very strong. In fact, one of the things that I'm going to be showing you is a little cup. For a caster that is a filament print. Very easy processing. The disadvantage though is detail. So smaller parts, like I'm going to be showing you some smaller parts, some flanges and so forth. That's more for resin printing. That's highly detailed, but the disadvantages are mainly in processing. It's just more of a hassle.
Can the same machine do both?
No. No, it's a totally different process. So filament printing, by the way, it comes on a reel. Would you mind, Ben, grabbing a bottle of resin and a reel of filament? So lots of different types of filament. Ben can talk about the different types of filament. There's some that are more rubbery. There's some that are more for strength. There are some that are more for ease of printing. Lots of different type of filament. It just comes on a reel, and the 3D printer, if you saw it in there, it just pulls it down, and the nozzle is very small, and they keep getting smaller as the technology progresses. So currently, our nozzle on our filament printer is at 0.4 millimeters.
Yep, that's the most common.
Okay, so that's
Here?
sure.
Table, maybe?
So here is a bottle of resin.
Is it liquid?
It is liquid, yeah. So the way the resin works is it's a UV cure. So kind of like when you go to the dentist and you get a filling in your tooth, and then they put that UV light in there, and it cures instantly. That's the same idea as this. So it's UV sensitive, and so the print plate, it comes down into a goo. That's the resin. And it basically touches the bottom of the bottom surface where there's a UV light that cures in very precise patterns onto that 3D onto the plate, and then it rises up a fraction of a mil, and then it does it again, and then it rises up and it does it again. So a tiny little part like this that I'll be talking about here in a minute. This is well, I'm not going to tell you what it is. I'm going to see if you know what it is, and no cheating, Jake. Jake knows what it is. So that little part there, we printed it in this orientation, in the thinnest orientation like that, and it was maybe 200, maybe 100 layers, something like that. And it took about an hour. So that plate is just rising up ever so slightly, and each layer is curing UV light.
That one part took an hour?
Yeah. Well, I printed 100 of them
On the same level.
and I probably could have fit maybe about double that. I ended up doing 100 in one print. Took about an hour.
And then you cut them apart or something?
You know what it is?
I'll show you. You do know what it is?
And how long did it take to do all 100 of them?
That 1 hour. It does all of them. It does all of them at the same time. Yeah, and you could probably fit probably 200 on the print plate that we have. So the advantage. Anybody know what that is? Adeline knows. Yeah. Yeah. So this one, we'll get into it more. That's a damper head, and damper block. And so the advantage of doing it this way is because this is a Steinway that has over dampers, and we were replacing all of the action, the entire action, everything except I wasn't able to find the over dampers. So we replaced all of the damper blocks except for the ones with over dampers. There were 6 of them or something down by the brake, and we took very precise measurements. When designing in CAD, you can get down to a fraction of a mil, and so the precision is extreme. Super cool. Okay, so just kind of brainstorming some ideas. The first one, I think the biggest reason would be obsolete parts. Working on 300-year technology, right? Most pianos that we work on are not 300 years old, but a lot of them that we work on are 19th century, and so lots and lots of totally obsolete parts that we're working with. Or in the case of the Nordiska, we're going to talk about that in just a second. Okay, one-off specialty parts. I was asked. There was a mover in Maine, and we're going to talk about this in a minute, who I guess they lost a leg. And so a piano technician in Maine contacted me. I think he saw something online, maybe saw some of my videos and saw that we'd take on crazy one-off projects like this. He contacted me and asked me to build a part, or build a leg rather, from scratch. And so that's very much a one-off specialty thing. And there are lots of different components to that. We're going to talk about that later in the presentation. Hard to find parts. I guess that's similar to obsolete. Okay, same day. Sometimes you don't have the ability to wait for a shaft order for a week or whatever, and if you're good at CAD, then you can probably have that part within, depending on the size of the part, within an hour or two. And then. Okay, specialty woodworking. Okay, so a lot of pianos, right, that are built in the 1890s, a lot of the uprights especially, they've got those filigree front panels, and a lot of times they're very fragile, and so there'll be a part missing, a piece of wood that's missing, or on legs, a lot of times there'll be carving that is very hard to duplicate with wood. Or as you'll see, one of the parts that we have, there's an entire piece of trim that was missing, and so we duplicated the trim. We'll talk about that. And then more economical. I'm not sure. I put a question mark on that one because I don't know yet. It's still too soon. I'm not planning on, by any means, on all the pianos that we're rebuilding. By no means am I planning on 3D printing parts for all of these. I think for now we haven't refined the process. I'm also not totally certain, that I'm going to be charging, thousands of dollars to rebuild somebody's piano with an experimental process. So far, so good, but more economical, I don't know. Yeah, is it going to crumble like spinet elbows? I don't know. I doubt it. I think the formulation of plastic today is totally different than the formulation of plastic in 1930. But so I'd be surprised. What's that? Say that again.
Lives forever in the landfill.
Yeah, that's right.
Live forever in the piano.
Yeah, I think that's right. Okay, so let's get started. So here's a Steinway. I can't remember what year that one is. Probably 1870, 1880, something like that. And so you can see right off lots of obsolete parts.
I'm sorry, would you mind closing the lid?
I was just thinking that too.
Okay, then down there we've got a Viennese action. And so here's just a kind of smattering of a few parts that we've designed and printed for different parts. Emerson, Knabe, Steinway, lots of these parts from 100 years ago or more that we've done. That one in the middle on the right, that's a back check for an 1895 Knabe, a very, very weird back check. I suppose that a modern back check would have been just fine, but you know, this option was at our disposal, so we duplicated that back check, and it works great. So we'll probably be able to duplicate that part. Maybe we'll glue it together just with super glue or something, and that'll give us all the dimensions that we need. And again, the level of precision that you can duplicate this with is extremely high. And so we'll print it and we'll see. I mean, the piano's no good. It's worthless now, so we may as well try. Okay. Anybody know?
Yeah.
Kimball. You got it. Okay, so this is a major hassle. You can get, yeah. Carl, if you could take a bow, please. Okay, major hassle. These brass flanges, they break, and there's not a replacement for that. Does anybody know of a brass replacement that I'm missing? Yeah. Okay. So those little parts. This is Kimball. Okay, so first thing we do is we design it in CAD. Okay, so what this is the side profile, and so I just take calipers and take all the measurements, all the necessary measurements, and again, it's more accurate than the caliper thousandths of an inch has the even capable of. So this is just it's a two-dimensional sketch of the side profile of the flange. Next is what's called an extrusion, and so then you take that sketch and extrude it out to the width, and now you have a three-dimensional thing that you can kind of rotate in CAD and kind of look at it from all directions. Next is the first cut, right down the middle there.
What do you mean, cut?
So this is the entire piece, the entire profile if it didn't have any cuts, and then the next one is to make a cut that goes all the way down.
In
just
CAD, not on,
yeah, all of this is CAD.
okay.
Yep. Yep.
Not on a saw.
Nope. Not on a saw. Not in the physical world. Okay, then I don't know if you can see it. It's kind of hard to see, but there's a plane right here that runs at an angle. Can you kind of see that? Okay, so that plane was just, you can create a plane based on lots of different parameters. The parameters that I used for this was you can make a plane based on 3 points, right? So 3 points in space is all you need to define a plane. And so you can just click, I want this point, and this point, and then it'll automatically give you a plane. And that's the next cut that was made virtually. And then it turns to the side, and here again, just get all of your dimensions here. The dimension of the circle for the bird's eye, or the center pin, I guess. Okay, and there you have it's squished a little bit. You get the idea. And then the screw, the exact dimensions of where the screw goes. And there's a little chamfer for the screw. And there's the finished part. And there's the finished part next to the real thing. And so this whole process to do it in CAD probably took maybe half hour, something like that. Someone like Ben could probably do it in probably 10 minutes. Ben's really fast on CAD. But me, it took me about half hour. Okay, so there's the resin. The thing that I'm holding there, that's the print plate, and that's so I've got it off and then turned upside down for the camera. You can kind of see the goo to the left, and the goo is kind of, it's sliding down the print plate. So you can see what I was talking about earlier, that this was 100 that we printed in an hour, and I probably could have fit about double that on the plate. So you can see it all still covered in the goo.
It looks like they're like on there randomly. Is that optical illusion, or?
No, they are. Yeah, there's a second program that you export the CAD file to. It's called a slicer, and part of that, like, I could take the time to individually place, and that would be more space efficient, to place every single one on the print plate, and then really squeeze it and get, maximize the print plate.
Virtually or physically?
That would be virtually.
Yes.
In the slicer program.
Okay.
But I'm not even using the full plate anyway, so I just had the computer automatically, I said I want 100 of them,
Yeah.
and the computer automatically just
Dump them anywhere.
dumps them anywhere. Yeah.
Is the goo reusable?
It is. Yeah. And there it is, pulled off the print plate.
So is that like that's a rigid, that's a physical thing, a picture of a physical thing, right? That's
Yes.
not yeah.
Yes, that
When
is.
you pull it off the print plate, is that whole sheet like rigid, or is it like a rubbery, flexible?
It's plastic. So that is resin. So it doesn't just print the parts directly on the print plate, but it prints supports. And then below that, under the supports, is just a solid kind of giant support for the supports. And then on top of that is the part.
How do you get them off the plate?
Just comes right off. Yeah, just kind of peels off the plate.
Really?
Yeah.
You have to,
Oh, and then that's the IPA rinse.
or
Okay, so as far as volume, do you know, Ben, which one is more what one is more cost effective, resin versus filament? The filament. You get far more print volume out of the filament.
Yeah.
So a roll of filament,
Definitely for different applications.
or yeah, sure. But roll of filament is $20 or
$10 if you buy bulk.
yeah. And then a bottle of resin. For cheap resin, you can get they sell it by the kilo, and so you can get a cheap bottle of resin for $20 or $30, and you can get so this one is a like an engineering resin is how they advertise it, and it was $90 for a bottle. And to give you an example, like these 100 Kimball damper flanges, it used 50. What's the milliliters? Is that right? So there's 1,000 milliliters in a kilo, and it used 50 milliliters. So 25 of those milliliters were used approximately for the parts, and then 25 of those milliliters were used for the supports. And again, that's why I'm not so sure about being cost effective. This full print was 50 milliliters.
yeah, so a very small percentage of the bottle
So 5% was used for the print.
for that print.
So, and that was $90 for that.
It's pretty cheap.
Okay, IPA rinse, that's isopropyl alcohol. That's what rinses it off. And by the way, I don't know if you saw it in the 3D printing room. That little bucket that I'm about to put it in there, it's an ultrasonic cleaner. So you just put it in, and it's filled with isopropyl. So it goes in there, turn on the ultrasonic, and it just buzzes for 10 minutes, and then your parts are clean. And then there's a second IPA rinse that's like a second wash. And then Duncan, you're asking about this. They just pop right off very easily, and it's a very satisfying pop. And then they go. So this is just a little. I think for like a store window, for like a jewelry case that just rotates, and then Ben just took a cardboard box and put it on top, and some UV lights, and that cures for just a few minutes. Okay, and there's the final product. Of course, we still have to bush it and put a spring on it. Okay, one-off specialty parts. There's that leg that I mentioned. So this was the picture that this technician in Maine sent to us. He said that these movers, they lost one of the 3 legs. Can we duplicate this? And so I said, absolutely. So I asked for a couple of measurements, like I asked, for example, for the absolute precise location of the holes for the bolts, obviously the height, and that was pretty much it. So you can derive all of that from the picture. If you know the height, it was 25 3/4 inches, then you can derive all of the other dimensions. Okay, so first thing, take measurements. So Larry, there it is. And there's taking some more measurements.
Wow.
What are you laughing at, Ben?
Right off, you're quick and dirty.
Yeah, it is quick and dirty. Yeah. And then and part of this I just went down to our cache of casters and found a caster that looked relatively similar, and then I took measurements down there at the bottom of the orientation of the holes for the screw, the screws in that little caster. Yeah, there it is. So that's the caster that kind of seemed to fit. If they complain about the color, I will say, deal with it. Okay, so here again, designing in CAD. I don't know if you can see that, but this is the first thing that I built actually was the rings. So that's half of the cup that this goes on, right? Because one of the like on the Kimball flange, we were able to extrude it, right? Make the picture of the side profile of the Kimball damper flange, and then extrude it out to the width of the flange. Whereas this is a cylinder, and so we make half of the damper flange, and then it's going to do what's called revolve, right? So it's basically an extrusion in a circle, and all of those dimensions are derived from taking these measurements. Okay, so there's the revolve. That's the first revolve, and then there it is. Like I said, you can kind of like look at it in 3 dimensions. And there's putting a hole in the top, holes up and down. There's I don't know if you can see it. There's a triangle, so an equilateral triangle for the holes there, and then put the holes on the thing, and then there's the thing, and then there it is. So that's filament. We talked about resin. This is a filament print. This took 3 hours to print.
Something like that, yeah. It's solid, 100% solid.
Yeah. And there it is. Very satisfying little snap. Check that out. Okay, so the first print that we did for this was in resin. There it is on the print plate. By the way, it's yellow because it blocks out any UV light. The only UV that gets in is the UV that it wants on the go. There it is. You can kind of see the supports there at the top. There's the print plate off.
It just snaps off that.
Yeah, the whole thing just kind of snaps right off. And then there it is in the proper orientation. No, sorry, the first one was the orientation. Okay, but I didn't really like that. I didn't like the resin, so we opted for filament instead. IPA rinse. You can kind of see the ultrasonic little waves in there. And there's the second rinse, UV cure. Okay, so there's the final product of the resin. That's before plating of this part, and so we tried filament instead. There it is. That, like I said, that took about 3 or 4 hours to print that. Okay, Ben, do you want to talk about the plating of this piece? This is not paint. This is brass.
Yeah, so the first coat is a paint. It's a nickel conductive paint.
It actually has nickel powder in.
Yeah, it's got a bunch of nickel powder that's conductive because the surface needs to be conductive in order to electroplate onto it. So after that first layer of nickel paint, then we can plate a thick layer of copper onto that.
Copper is the top left.
Yep.
It's hard to see, but if you look at the pedal underneath it, you look at the color between the two. So the pedal down here, if you look closely,
Use your mouse to point.
is very yellow, and that's copper.
Use the cursor on your mouse to point.
There's the copper. There's the brass. And this is nickel. Okay?
Yeah, and then nickel on top of the copper, and then brass on top of the nickel.
Why do you do it that way instead of just brass, 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 or just brass?
Well, the brass is thinner because it's a much more difficult chemistry, and the copper is much easier to build up a thick layer, so you can have a thick, strong plate. And the nickel is the best for buffing and polishing, so you can get a nice surface. With the copper, and if you try buffing, polishing copper or brass, you can get residual scratches from the buffing wheel because they're so soft. But polishing nickel, you don't get those scratches left over.
So by the way, Ben, what's your turnaround time for a set of piano parts?
Generally, it could be a couple weeks. I mean, if it needs to be a rush, I can do it the same day.
Okay, cool. Okay, so the rings, there it is zoomed in. The rings above the little round cup caster, those, basically the same process where it's designed in CAD. This one is not going to be supporting any weight, whereas the cup for the caster will be. That's why the cup is solid, and then the rings are just purely cosmetic. If you look closely, you can see that so this is hollow, and we designed in these little holes so that the resin will be able to come out. It's not solid on the inside, and also the IPA rinse will come out of the holes. I can pass that around. So there's this is a that's a resin. Okay, same process. So there it is coming out of the resin. Close up, you can see the supports. There are supports on this one. The orientation that we had this one in, we needed supports because there's an overhang, and you can imagine that with an overhang, it's going to droop if it's not supported. So that's what these are on the side. It's hard to tell in the picture, but it's kind of angled. It's angled like that. Okay, there it is going in the ultrasonic cleaner with the IPA coming out of the IPA. Second bath, UV. There it is. There it is on the thing. Okay, so the other reason was parts needed the same day. This is an example. I had a lady that she bought a piano, and when somebody wants to pay me $10,000, I want to treat them with white glove treatment. She asked me for caps. She didn't like the fact that you can see the bolts, and so I said, I can do that. So this one took me probably 5 minutes to design in CAD, and then print it off, and because you're dealing with calipers, you just do the inner dimension of the bolt hole on the legs, and then first time right out of the printer, it just pops right on there. So we'll be getting a CNC router within a couple weeks. It's going to come, so that'll be able to do that. Okay, so specialty woodworking, stuff like, a lot of times this stuff, where these pianos are 120 years old or more, at some point somebody broke one of these off, or down here in this section, or this music desk, there's bound to be a piece that is broken off, and so that can very easily be duplicated, created in CAD. Okay, here's an example. What we're looking at here is, this is an Erard, and this is the back corner. This is this corner of this Erard that's missing that piece of trim, and so there again, we took all of these measurements, and part of CAD, what you can do is you can import an image into CAD and then just trace around it, and then you've got your exact match. So there's the, and it's a similar kind of, it's like a cross between extrude and revolve on that. Does that quarter turn. There it is, designed in CAD. Okay, there's, to take a picture for this presentation, the piano is currently on its side, so that's the side. There it is with the piece pushed up against it. And there it is from the bottom. You can see that it just kind of goes around there. And oops. Okay, and there's the piece, you know, faux wood, something like that to make it blend in. Okay, this Hallett Davis is turn of the century, and this entire side of the piano was missing this trim, and as you can see, this is very unusual specialty trim. Oops. So here is the trim that goes around, and it just ends right here. So this entire side of the piano right here doesn't have any trim on it.
By design? Oh, it was
Just missing. Yeah. So there it is, again duplicated right here. Okay, so there it is. Next to the part that we had, and it matches right on. Okay, so the same way that this is done on the Erard. This photo, this was actually the photo that we used in CAD. So you import the photo into CAD, put it on your plane that you choose that you want to, because there's 3 planes, right? So put it on the plane. This would be I guess the Y plane, and then trace it to create the profile exactly around. You know, you can just place dots along the photo, and then based on the measurement taken from the piano itself, you can size it. You can change you can calibrate it to be exactly the right size. And then because this it's essentially a quarter turn, so rather than extruding it straight like the Kimball damper flange, or extruding it around in a circle like the cup, it's a quarter turn extrusion. And then similar to that, a lot of these patterns here, those can all be duplicated. So just measure one cycle and get all of the exact measurements of that one cycle of the pattern, and then just repeat that cycle. So this required several prints. So we have some prints that weren't quite right. So most damper flanges that are double are from Steinway. And so on the Steinway, the profile here is kind of a weird shape, right? And it only fits on the Steinway. What's that rail called? What is it? The profile? Yeah.
Rosette.
Okay. So whereas this one, it just has the normal indentation there, or inlet, the square, yeah. And so I can't remember if this was the Emerson or the Knabe.
Come out bush too.
They come out bushed.
Yeah.
Yeah. Some other things that we've done. We had so Mason Hamlin. They've got a kind of a trim, kind of a half round that goes across the side. We had one Mason Hamlin that was missing its trim piece here, and it did a 90, I think. Or did it curve? See if I can find it. So here's just kind of a collection of a few parts. This is the back check. right here. And then here's that double flange. This is the Knabe right here. And then there's the little stamp with the logo, so we can just size that and put it on the side, you know, for fun. I think, you know, if you were just to look at cost, it would probably be cheaper to print it. But when you take into account, especially when bushing is involved, it's probably a lot cheaper to just buy it. And you can see, if you look closely, it even shows you, because this is the screw, this is the set screw, right, that holds the damper wire on. So you can see down here the hole that dead ends into the set screw. So if I zoom, let's see, there it is. And there's the little indentation that holds the overdamper in place, and then the overdamper goes right down in there. And so so there you can see that oh shoot. Anyway, so the distance that come on, there we go. So the threads come through here, and so the distance that the overdamper can go through is a little bit deeper than where the set screw goes. And then put on these little ridges because yeah, I was concerned about glue, because that's an unknown. Those ridges look large here, but in real life they're very fine, and so I figured that increases the chances that glue will stay long term. These are the pedals that and then here again, because we're dealing with obsolete parts, right?
The design was very unique.
Yeah, I mean, I guess you could find some solution with new pedals, but so Ben, this is Ben's work. I am not taking credit for this one.